There are, of course, many ways people will argue to you that category theory is useful. I can't say that any of those reasons motivated me to stick with it for almost 40 years. The common denominator of everything that everyone will show you about category theory is that there is lots of pictures. I got into it because it was the least bureaucratic. It wasn't command line. We were drawing diagrams. And in the meantime, it's even more like that. Remember that mathematics was first constructions with compass and ruler. But on the other hand, these constructions require interaction with the medium. You know, Archimedes needed sand to draw his circles in the sand. You need paper to multiply large numbers and fit them in your head. And it all got pretty bureaucratic when they invented printing and when, you know, people started stuffing math into lines and programming was 80 characters per line. But in Archimedes' time and now with the computers, it isn't. You can do it at least in two-dimensional space. So you reason a little bit more flexibly with diagrams. And the job that my abstract came about by me sending an apology email to Spencer why I didn't provide an abstract and telling him I could maybe tell about how I've been teaching second-year students theory of computability and complexity using these pictures. And I had to do that because my job is to teach them security. We need to defend ourselves. And even security, I've been teaching people for a long time, and after about 5 years, people you taught security come back to you and they say all these tools, forensics tools and protocol designs tools that you taught me in your course, they're not used anymore. I had to learn how to use new tools. The life expectancy of a security tool is not more than 2 or 3 years. Then you ask yourself, well, why is that? And then you realize security is actually principal agent problem. You know, someone comes to you and they say, well, Bob wants to attack you and he'll steal $10 from you. If you give me 6, I'll defend you. And every 2 or 3 years, I'll give you new tools for that. And then if you think about it and you pay them, then they realize, well, actually, if I'm charging him only $6 and I'm saving him 10, I'm not maximizing my profits. I should actually charge him at least $9.50. So you end up in this situation that you're teaching students stuff which has, you know, it has vested interest to not last. So you have to teach them not how to use the tools, but how to learn to use the tools which don't exist. And so therefore we have this sexy area, security science area. You don't teach them security engineering anymore. Or, I mean, most people do, but you know, kind of to try to teach them what they will need, we teach them how to learn. So not tools, but science. And what are the problems there that you encounter? Well, you know, security is a science, but on the other hand, it isn't. Science is, you know, difference between engineering and science. In engineering, you build something that doesn't exist yet from a theory. And in science, something exists and you want to build a theory. And here you have theory about something that exists but doesn't like to be observed. You want to help NSA with scientific contributions, and the scientific problem doesn't like to be observed. And the second problem is that it's all about complexity. You know, you want to use one-way function so that the attacker has it a little bit harder or a lot harder than you. And then that science itself becomes complicated. And that is where my pictures kick in. And that's what I want to tell you about. So here's, you know, lesson 1 in some security course. you want to define what is secrecy. And this notion of secrecy evolved a lot. Shannon defined it for the first time in 1946. And every year or so, they realize that it's not sufficiently strong definition. So this is the taxonomy, which I'm going to now intimidate you with to show you that we can do better with pictures. So this is, to define secrecy, we want to define first the object which needs to be secret, a cryptosystem. So you have 3 or 4 types: plain text, ciphertext, keys, and random seeds. And a cryptosystem is a triple of algorithms. One generates keys, one encrypts, one decrypts, and they are all randomized. Encryption at least needs to be randomized so that if you're interested in the meaning in the ciphertext of the plain text lounge war, you can just encrypt it and then wait for that. I imagine that you know what this is like, but it needs to have 2 properties. One is that after you encrypt your plain text, you can decrypt it. You can get it back by using the key. So that is the functionality of a cryptosystem. Secrecy of the cryptosystem, and here is Shannon's definition, is that if you see the ciphertext and you want to guess the plain text, the ciphertext doesn't give you any advantage. Your chance to guess the plain text if I give you the ciphertext is the same as your chance to guess the plain text if I don't give you the ciphertext. So they are statistically independent, said Shannon. But then you actually need to calculate. Even if I give you the ciphertext, if it's really, and they're not statistically independent, but it's really hard to compute the plain text out of the ciphertext. So for all algorithms, you would like it to be the case that that algorithm will not give you a better chance with the ciphertext than without the ciphertext. So that is making it a little bit more modern. So that's the first step in the refinement. But then if you look at this definition, if I'm able to guess half of the plain text, but not all of it, then it's secure. If I'm able to guess 3/4 of the plain text, but not all of it, it also satisfies this definition. So then they refined the definition, strengthened the definition, and said, how can we need to require that your chance to guess 1 bit of information about the plain text doesn't improve. So how do we do that? So suppose that we randomly select 2 pieces of plain text, and then the encryption algorithm flips a coin and encrypts one of them and gives you the ciphertext of that. And it's your job to say which one they encrypt. So that way you're guessing just 1 bit of information about the plain. And again, a la Shannon, we want that your guessing capability does not increase with your knowledge of the ciphertext. Okay? And then back in the 80s, so this is the algorithmic. We take into the account that it may be algorithmically hard to do this guessing, although statistically the correlations exist. And now we enter modern cryptography. In the 80s, Goldwasser and Mihaly defined something equivalent to this definition. So it is indistinguishability, chosen plain text attack. You choose these 2 plain texts. So they're not randomly chosen out of the language, but your algorithm gives 2 plain texts. The encryption algorithm flips a coin, gives you gives the ciphertext to the attacker. The attacker has chosen the 2 messages and knows the ciphertext of one of them. Which one is it? And normally, the probability, guessing probability for the coin flip is 1/2, and we would like it to not be better. And then usually the attacker actually has the encryption oracle available. The Enigma machine was available to the cryptographer. So before forming the two messages, the attacker can play around with the decryption oracle. The attacker can take various ciphertexts, polynomially many of them, decrypt them, and then on the basis of that form the two messages and get the ciphertext. And then the attacker needs to guess one bit of information about the plaintext. And finally, the definition, which the requirement of the 90s and 2000s is that the attacker actually, even after they get the plaintext, even after they get the ciphertext, they can again play a little bit with the decryption oracle, except that they are, of course, not allowed to submit the ciphertext to the decryption oracle, and then they get. So this is in CCA2. So observe how strong and demanding this is. If I give you an encryption of 10 hours of video, you are allowed to flip one bit and submit that for decryption. That should tell you nothing. That should not give you one bit of information about the plaintext. So I hope I've intimidated you a little bit. This is what I'm supposed to teach second-year students. They of course didn't like that. What is the problem with it? There is cryptography. Modern cryptography lacks abstraction. You know, we all, when we learn programming, we all learn about virtual functions. Hide away the irrelevant implementation. You know, this revolution of programming has not happened in theoretical computer science. They're still working with low-level models. These definitions are still in terms of Turing machines and circuits. So this hiding irrelevant implementation details, which we see on Picasso's sketches of Boole, closing it into the black box, it didn't happen in theory. Another form of abstract paintings is that you can play with the black box, but cryptography is something like this. You don't hide things into the black box. You drown in the structure. And can my categorical pictures help with it? Well, I did my best. I have no idea how the time is going, so you wave at me when I'll
give you 10 minutes.
Yeah, well, or 5 or something. Yeah. Okay, so can I draw my circles in sand? Computer science in 4 pictures. Now, this is my from my second year course, and you can find lecture notes on this website, which are extracted from what I hope I'll deliver as a textbook by the end of the year. Okay, so concept number 1 is induction, or otherwise known as counting. You generate numbers by counting, and an important thing about it is that you begin from nothing. Counting begins from 0. When they told that to 17-year-old von Neumann, then he said, I actually don't need anything except nothing. I can counting nothings. And he published actually the paper from which then Gödel extracted his construction of internal models of ZF. Each number is the set of its predecessors, and the predecessors are all formed of the empty set. And moreover, and here we step into computation. Computation is about representing infinite processes by finite means, by writing down finite specification, infinite sets. All that we need to know to continue counting forever is that the next number will be the union of all its predecessors and itself, and you always have one fresh thing. You can add one more layer, and so this is all very basic. This is how computation has been going on forever. Let's see where do the pictures take us with. So here's the basic inductive definition of, which as soon as you have been counting a little bit, you will write this down. I can count on as long as I like, and in order to get n, I need to make n steps. And the induction schema is basically the implementation of that. And we all start courses in computability theory by an instance of induction schema, by recursion schema, which is just induction with a parameter. Now in pictures, and then functional programming replaces names with constructors, and we get a step closer. So this is the induction schema, what it would look like in any functional language. This is these are banana brackets which they use, and here is all of that with the simplest kind of pictures. We have a constant b, and we have an endomorphism beta, and the inductively defined function needs to satisfy two equations like this, and we replace the command line equations on top by pictures like this, and now we are doing category. Now we don't need to write a sign equal, but we do a picture, and we can go from this path to this path, and that is our equation. And if you go a step further, then you put morphisms here, and you have two categories where you're chasing these equations as a kind of homotopies, and a Poincaré dual of such pictures would be the string diagrams. And now we're doing this same computation business in pictures. Okay, concept number 2 would be co-induction. Why do you need that? Well, in order to add two numbers inductively or recursively, in order to add m and n, you need to count up to m plus n. You first count to m, and then you count to n. So can I do better than that? Well, of course I can do better than that. I need a two-state machine, which will remind me, and the state will tell me whether I'm carrying or not. Then we have the children's addition algorithm or addition algorithm, which you and I use when we're adding numbers, and for that I only need a logarithmic number of steps. So the co-induction schema is basically state machine. This Q is the states. So I have some finite number of states, and I have the state update and the output, and the co-induction is the same specification method of infinite processes by finite means, and you don't have to read this because in pictures, in similar kind of pictures, it would be something like this. This is co-induction for, I guess, Mealy machines. If you move this Q to the other side, this would look like a coalgebra, and the co-induction gives you the canonical representatives of the behaviors of your state machine. And now we don't need to count to n plus n to add m and n, but we can't multiply arbitrary numbers because our machines have finitely many states. And if you ask yourself how many states do I need in order to encode my multiplication algorithm, I can't. I need unbounded memories. Finite number of states gives me bounded memory, bounded by the number of states. So that is what led Turing to add unbounded memory to finite state machine tape. He can write on the tape as long as he likes, and lo and behold, now we can even multiply. And okay, so I don't know what I'm doing here. I guess I'm developing a little bit a different notation. This definition, but concept number 3 is the computer. And the essence of the computer is that unlike iPad and iPhone, you can run programs. In the same kind of pictures which allowed us to represent induction and co-induction, these string diagrams or pictures which are dual to the traditional categorical diagrams, all that you need is that every morphism in your category, so there are universal computers in your category. So there is which people in programming languages call interpreters. There are interpreters and there are partial and they are specialized for universal evaluators and partial evaluators. And our category is a computer for every morphism. Let's say here, which takes two arguments. For every computation, there's a program. For every morphism, there is a constant, such that if you run that constant, if you apply your universal evaluator on that constant, you get your arbitrary morphism. And you can partially evaluate things. If I give you one argument, then you can evaluate your program on that one argument, and the specialized and the partial evaluator will give you a program which will be sitting waiting for the next program, currying or uncurrying, so that you can actually get computably indexed families of programs. And amazingly, this is all you need for a Turing complete model. This is the programming. This is the simplest categorical programming language. There's two commands and one axiom. So the fundamental theorem of computation, which says that this is all you need during completeness, is what Kleene needed to work through, and that is second recursion theorem. It says that every computation has an extensional fixed. So for every program, for every computation which takes something of type of program, there's a fixed program which, when you run it, will give you the same as if you plug it into the computation. Using this, you then capture everything else. You capture recursion, you capture unbounded search, and that is already Turing complete. Or using this, you represent Turing machines themselves. Here's the proof of Kleine's second recursion theorem in picture. This is the fixed point, the partial evaluation of the program encoding the pre-composition of your computation with a partial evaluation. That is that program you apply to itself. Copying allows you to partially evaluate it, and that's it. So this is computability theory in 4 concepts. So where does this bring us with respect to security? So here's Shannon's definition in the same language. It looks a little bit simpler. What it says is encryption is this computation which takes plain text and gives you cipher. We either interpret conditional probability in joint probability, and now we say the probability that I will guess the plain text out of ciphertext does not depend on the ciphertext. So it will be, so this is the source of plain text. This is Bob's dictionary of languages, of sentences. So this is Shannon in picture. The picture is the same, but the category is different. Now we go into the category what some people would call assemblies, where all morphisms are computable. So now this probability, this guessing probability needs to be some algorithm, and it again says for all possible algorithms, the outputs that they will give out of the encryption algorithm will be just the distribution of the source. So now here's the ciphertext only attack, where you require that not a single bit of information can be given. So now we have the source is taking two messages and a random bit, and this is a projection. The universal evaluator works as a projection if we suitably define true and false. So it will give you one of the it will project out one of the messages encrypted. You take the decryption. The requirement is that you are perfectly welcome to throw everything away and just to guess following the frequency of your sentences. That is what is required from ciphertext only attack. If you know the plain text, so if you tell the algorithm what the plain texts are, the requirement remains the same. And finally, here is the first modern notion of secrecy. The attacker generates the two messages. Okay, we could give the attacker some algorithmic information as well if we wanted, but in all cases, the flow of information has to be disturbed. In other words, the bit no information about the distribution, no statistical bias on the bit should be induced by the availability of cipher. And the attacker becomes a